So part 3 is model training. So I will cover fair training, and Jae-Gil will cover robust training and representational learning. So until now, I was talking about data validation and data cleaning, but there's still no guarantee that your data is perfectly fine before model training. You may still have to cope with data bias and poisoning during the model training. So there is this popular article by an organization called ProPublica that talks about the software called Compass. This is a tool that's used by US courts to predict whether a defendant has a chance of committing crime in the future. And the problem is that Compass overestimates the chance that Black people will commit crime in the future, also known as recidivism risk, compared to white people. And the problem is this is much higher than reality. And the reason is that Compass was trained on biased data, which is biased towards Black people committing crime. So there is a well-known saying that garbage in, garbage out. This means that biased data results in discriminatory deep learning models. So when training a model on human biased data, it's like reflecting yourself in a mirror. So you can now see all the bias that was kind of injected into that data. So this is a problem, and many companies are starting to realize that they need to be more careful and responsible when deploying AI to the world. So to summarize the quotes by Google and IBM, Google says that AI has a significant potential to help solve challenging problems, but it's important that it's developed responsibly. IBM says that performance is important, but we also need to build, evaluate, and monitor for trust. So what are the key issues of responsible AI? Well, the first two are fairness and robustness. There's also the issues of explainability, value alignment, transparency, and accountability, and maybe more. And here, we're interested in the first two because they're very related to the data, and also the two issues are related with each other. So I'm going to focus on fairness for now. So fairness is a very subjective notion, and there are at least tens of possible definitions out there. And among the surveys, I personally like the tutorial presented by Suresh in PODS 19. So he categorizes the fairness measures into largely three groups. One is those that only use the classifier, representative measures called individual fairness. Another class uses classifier and the protected attribute, where the protected attribute can be something like race or gender. And the third group uses all of these three. So it also uses the training labels. So for all of these categories, for each of them, I'm going to cover the representative measures. So I'm first going to cover demographic parity, then equalized odds, then individual fairness. So I like to use a running example to be very concrete, and I don't even need to use a complicated model. I'm going to use a Perceptron, which is the most basic unit in a neural network. Now, this Perceptron receives input features. So let's say that we have three of them here. Race equals Black has the value of 1 if the person is Black, or 0 otherwise. Race equals White has 1 if it's a white person, or 0 otherwise. Previous crime is 1 if the person has a previous crime, otherwise 0. And this is a constant just to make sure that, well, our threshold is 0. So this is here for convenience. So now whenever there's an input data, we take the weighted sum by multiplying the feature values with these weights, the 2, 1, 1, minus 2, And if the sum is at least 0, the perceptron or model predicts recidivism, otherwise not. For example, let's say that we have this person, she is white. Let's say she did not commit a previous crime. In this case, the weighted sum is 0 times 2 plus 1 times 1 plus 0 times 1 minus 2, which is minus 1 and a negative number. So therefore, no recidivism is predicted. So the interpretation is that this person is white, has no previous crime, so no recidivism. What about this person? Well, the only difference is that, let's say this person committed a previous crime. So then the weighted sum is going to be 0, and which is at least 0. So therefore, the model predicts recidivism, and the interpretation is that this person is white, but has previous crime, so it's likely to reoffend. Let's say that this person, the last one, it does not have a previous crime and is a black person. So the weighted sum in this case is still 0, mainly because the weight for the race equals black feature is so large, it's 2 here. And so the interpretation is that this person has no previous crime, but is black, so is likely to reoffend, which is obviously wrong behavior, but I'm just putting this in for illustration purposes. Now, just to give you some basics for deep neural networks, so each of these perceptrons are connected to form this neural network where there is typically an input layer followed by one or more hidden layers, and then an output layer where you can use these final y values to make a prediction. And individually, each node, the output is going to depend on the weighted sum of the inputs, followed by some nonlinear function, but that's applied to this sum. And there are many design issues for developing deep neural networks. So building a neural net is partially art, part science. Before training a neural net to find the right weights, we need to make several design decisions. We have to decide how many hidden layers are there, how many nodes there are per hidden layer, and how to interconnect the outputs of one layer to inputs of the next. And other design decisions are what cost function to use. So this function is used to measure just how much incorrect a prediction is compared to the correct label. How to compute the outputs of each node, and which algorithm should be used to optimize the weights. And so all of these issues you need to worry about. And there are many references for helping with this, making these design choices. One reference that I find useful is from Yuri Leskovich, Mining Massive Data Sets. So now let's come back to model fairness. So I want to demonstrate a few measures so that you have a good understanding how they work. So this says that sensitive groups must have the same positive prediction rates. And so the formulation is as follows. So z equals 0 and z equals 1 mean white person, black person, or maybe male or female, or any two sensitive groups. Y hat equals 1 means that the prediction of the model is positive. So maybe you predict recidivism, maybe you predict whether to grant a loan, and so on. And demographic parity says that the probability of prediction being 1 must be the same for these two groups. And so this definition is not applicable to all all cases, but it is used by government agencies to ensure hiring fairness, for example. So let's see how this works for our data. So remember that we had two white people where for one person, the prediction was 0, one was 1. And so the probability of y hat being 1 is 50%. And for the black people, we had one prediction that was 1. So this is 100. So you can see that according to demographic parity, there is some unfairness going on. Now let's move on to the second representative measure, equalized odds. So here, the only difference is that it's the same as demographic parity, except that we now use the label information. So we want to guarantee this property when the label is 0 and when the label is 1. And so this is the formulation. The only difference is that we now have y equals a, where a can be 0 or 1. So y equals 0 means the person did not commit crime. Y equals 1 means that the label is 1, so the person committed crime. So going back to our example, now we have to consider two cases, when a is 0 and when a is 1. So when a is 0, let's say that these two people eventually do not commit crime. So then the positive prediction rate for white people is, well, there was 1, 0, so it's 0%. For black people, there was one positive prediction, so it's 100%. So in case 1, there is unfairness going on. What about case 2? Well, here, let's say that this white person eventually commits a crime. The probability is 100% because there's one positive prediction. Now, for the black people, my example was so small that I don't have data for this, but you can assume that, remember the perceptron always returns true for black people, so I can just say that this is 100%. So in this case, we have fairness for case 2. The third fairness measure I want to cover is individual fairness. Remember, this is the one that only uses the classifier. So the idea is that predictions for similar people must be similar as well. And that can be captured by this expression. So let's say that small d is some distance function among examples. So here, these two people are close together. These two are far away. And so for the close people, the similar ones, the predictions of the model must be similar as well. In summary, biased data results in discriminating models. And so responsible AI is this new kind of notion that's becoming critical, where you want to guarantee fairness and robustness to train models that are more trustworthy. So I covered several representative fairness measures, and you can see that fairness is a very subjective term, and there are actually many possible measures, even beyond the ones that I just covered. And this is an active area of research.